Hi Year 13. I have heard that Feynman diagrams were a little bit tricky for you and that you were asking Miss Knoll for help because you didn't want to ask me because you know I'm very busy, but really truly ask me any questions that you've got. I always have time to answer you. They are a bit tricky. I did worry that it was going to be a bit of an odd one to do as cover, but let's see if I can help explain it. Sorry, I'm just recording this on my phone, so it's going to be a bit wobbly. You've read these rules anyway, so they are diagrams that you either draw or you look at and you interpret, and one of the axes will always be time, and both are used on IB. So time can either be on the x-axis or the y-axis. Then we can represent different types of particles in our diagrams. Now, if we want to represent a matter particle, so things that you're used to, protons, neutrons, electrons, stuff like that, we always draw an arrow to represent them, and the direction of the arrow is always in the same direction as the time axis, and that arrow tells us nothing except for the fact that it is a matter particle. And then if we want to represent an antimatter particle, we point it in the opposite direction to time. Okay, so, oh, excuse my finger, the arrow direction only shows us what type of particle we have. That's why we have a direction on the line. Okay, and we know that when matter particles and antimatter particles interact with each other, we know that a boson is involved. Okay, so an exchange particle. Same with the decay process. We need a boson to do that, and I'll talk to you more about that in just a second. So remember that these diagrams are just a jazzy way of showing interactions between particles. Rather than having to write about it, we just have a simple diagram, although until you understand it, it's not that simple. So I'll give you an example first. We'll look at beta decay because it's good to recap this anyway. So if we look at beta minus decay, we have a neutron turning into a proton and an electron and antineutrino. Okay, and we know from previous lessons that the W minus boson is responsible for beta decay. Okay, now a neutron, you now know, is actually just made up of an up, down, down quark combination, and a proton is an up, up, down. So to go from having a neutron to a proton, all we actually have to do is turn one of the down quarks into an up quark. So that's the only bit that I'm going to show you on my diagram, just to make things simpler than having to draw extra lines, but I could do that. Okay, let me see if I can hold this somewhat steady. All right, so I'm showing you a Feynman diagram for beta decay now. I have put time on the y-axis. So what that means is that if I'm looking at the diagram down here, it's earlier in time than something up here. Okay, and I can draw dotted lines to represent identical points in time. So anything that lies on a dotted line is happening at the same time. Okay, so we know that a down quark is what we have to start off with inside of our neutron, and we know that what needs to happen later in time is it converts to an up quark, which you can see here. Okay, so I'm going to switch because I'm actually right-handed. So we want our down quark to be converted to our up quark. Okay, now we know that what happens in beta decay is at a specific point in time, so this middle dotted line, the down quark converts to an up quark, which we see later, via this exchange particle. Okay, so this is all happening at the same time. We have a down quark converting to whatever we have on the other side of our exchange particle, which you can see is an antineutrino and an electron. Okay, so this is an instantaneous switch between down to what we have going out here, which is up, and then we have an electron and an antineutrino given off. Okay, now this pointing down just tells us that this is an antiparticle. Okay, time is still progressing up the page. Okay, so at this point we still have our up, our antineutrino and our electron. Okay, and the rules that I gave you on the slides, where it says you have to have an arrow in and an arrow out, it's just for conservation. So you can see that at each end of the exchange particle, our boson, we have to have an up going in and something going out, and obviously that is also conserved on the right hand side as well. Okay, another simple example to maybe help is looking at annihilation of an electron and a positron. So this time, instead of having time on the y-axis, I've put time on the x-axis. Okay, so this is t is 0, this is some time later. Okay, this is actually the only time that we're really interested in. Okay, this is the instantaneous point in time where these two particles and antiparticles meet, interact, and produce my photon. Okay, so we're not really interested in before, we're only really interested in looking at where things meet, because that's where we have interactions. Okay, so we've got our electron and our positron meeting at this point in time, and then subsequently they no longer exist. Okay, there's no electron or positron after this point in time, and we just have the photon, and we've got annihilation. Now remember that in the exam you might actually get it on the x-axis instead, but all I can do is I can turn my post-it note around and it still works. I have time is 0 on the left, here's my time of interaction, and sometime later this is what I've got. Okay, so it works in both axes. Okay, just to make sure I've gone through some of the slides, just in case they were still a little bit confusing, those letters there, Q, L, B and S, are for charge, lepton number, baryon number and strangeness. So it's similar to the previous lesson. It just means that before and after the interaction or point in time, those things have to be conserved. Okay, so here we again have annihilation of an electron and a positron forming a photon, and time on the, in this case, is on the x-axis. Hopefully you can see that. Okay, so the dotted line just represents an instant in time. Let's see what else I had. So let's have a little look here. What is this electron absorbing? Okay, so time is on the x-axis. Okay, so in fact, let me just grab the draw tool 1 second. So I know that if I draw a dotted line here, sorry, I'm trying to look through my phone screen, that's not very helpful. That is an instant in time, okay? So I have an electron absorbing a photon. That just causes the electron to move off in a higher energy state. So this on this side is still an electron, and it's just a higher energy state electron now because it has absorbed energy from this photon. We can see that the photon no longer exists after this point in time, so it must have absorbed that energy. Okay, how can you tell that the diagram on the left shows an electron absorbing a photon, whereas the diagram on the right shows it emitting? Okay, so it's a similar thing. So again, if I'm drawing, this is an instant in time. Sorry for my very dodgy, quick dotted lines. Okay, so on the left, we have the photon before the interaction point and not after, so it disappears, so it has to be absorbed. Whereas before the interaction point, on my vertex, I don't have a photon, sorry, I just have an electron, whereas afterwards I have an electron and a photon. So this electron here is in a lower energy state. Okay, so we can see that time must be on the x-axis. Okay, and so time is going from left to right. Okay, we always know this because it's either on the x-axis or the y, and we can see that it's the x-axis in terms of the movement we see with our arrows, but because we have positrons, so they're antiparticles, they point in the opposite direction to time. So let's go for our dotted line to show this interaction point at this vertex. Okay, time initially what we have before the interaction is a positron and a photon. And then after this point in time, to the right hand side of it, we don't have it anymore. Okay, so it must be absorbing. Okay, what have we got now? Two particles interact and annihilate. A photon is produced. What are the two particles? Hopefully you've recognised by now that we've got an electron and a positron. Okay, hopefully you can see if I switch from slide 24 to 25, it's the same diagram, but the other way around. Okay, so again, let's go for an instant in time. I have a photon before this point in time. And then afterwards what I have is a positron and an electron. Okay, so this is pair production. So we've got a photon converting into a positron and an electron. Sorry if my camera skills are very wobbly here. I think that's all I'll go through now. Oh no, maybe I'll have a look at this one. Let's have a quick look. Okay, sorry that video cut off. I got a bit wobbly. Right, let's have a little look here. So what process is represented here? Okay, so we are going to have a little look. We've got time on our x-axis, and what we can see is an electron and a second electron moving together in space. Okay, so if you think about it, oh, sorry, that's my time axis. Sorry for the very dodgy drawing. And this is my space axis. So this is where something physically is in space. Okay, so initially the electrons are further apart, and then they're getting closer together. Okay, that distance between them gets smaller, hopefully you can see, as time goes on. Now we know that when two electrons get closer together, they repel each other. Okay, so this interaction here is actually a Coulomb repulsion between two like charges. Okay, and it's just that the boson responsible for that is a photon. Okay, so you've got Coulomb repulsion because you can see that they then move away from each other again. So that's how I would represent this one. Okay, last little bit, I'm going to just quickly look at the IB questions. All right, so in this one we have a Feynman diagram showing a particle interaction, and it says that that is mediated through the W minus boson. In this case, you've got a dashed line instead of a wiggly line. Same thing, it's fine. Which particles are interacting? Okay, so what you have to look at is the interaction point is here in time, okay? So before the interaction point, we have X and Y. So those must be the two things that are interacting. That gives us C there. We've looked at beta minus decay, but what we need to have a look at now is beta plus decay. Okay, so instead of having a down converting to an up, we have to have an up converting to a down in beta plus decay. So time in this case is on the y-axis. So hopefully you can see the answer is A. Okay, we've got an up quark from a proton converting into a down quark so that we're left with a neutron. But this time we're going to need a positron and a neutrino created. So it's basically the opposite of a beta minus decay. So hopefully you can see that that one is A. And then last but not least, which Feynman diagram shows the emission of a photon by a charged antiparticle? Okay, we can automatically eliminate A and B, okay? Because the particles we have in A and B, the arrows point in the same direction as the time, and so that means that we have a particle, not an antiparticle. Okay, so that narrows it down to C or D. And we are looking at the emission of a photon by a charged antiparticle. So we're going to look at the vertex where they meet, and we know that the photon, so the wiggly line, has to come after that point in time. So hopefully you can see it's C, whereas in D it's before. Okay, so that's absorption. So C is the emission.